Okay, so now let's talk about the EM algorithm and its specialization to Gaussian mixture parameter estimation. So the EM algorithm is something that requires some creativity to apply to any given situation, but it's a general framework. So let me state the general framework. It's for basically trying to do ML estimation. So there's an observation X, a parameter theta, and I want to optimize log of P of X given theta. You want to max over theta, and basically that's my ML estimation framework. So in our case, the observation X will be a bunch of training data points, for example, X1 through Xn, and the parameter theta, for example, we saw already what it was for Gaussian mixture models. So we'll come back to that example in a minute. So for the EM algorithm, we have a situation typically when the actual ML estimation problem is intractable. Basically that this log likelihood function here is very messy. For example, you saw that for a Gaussian mixture, we had the log of a sum of a bunch of things, which doesn't really work out, right? So this is intractable, and the creative part of applying the EM algorithm to various situations is to come up with the concept of a hidden data that you don't see. You come up with it such that log of the joint density of P, X, and Z, basically the observed data and the hidden data given theta, is nice. So in what sense does it have to be nice? Basically, it should be nice enough that you can do some averaging. So let me just sort of state the algorithm, and then we'll talk about what nice means. So just like many of the algorithms we have seen already, k-means and then the Gaussian mixture algorithm, parameter estimation algorithms, basically the EM algorithm is an alternating algorithm, and it's got two steps that we alternate between. One is the E step, E for expectation. The idea is you have a current estimate of the parameters of interest, and we'll denote this by theta sub L, sort of the Lth iteration. And what you want to do is you take this log of this joint density of X and Z given theta, and you average out Z. So Z was the thing that made the things look nice, the log likelihood function look nice, and so the form hopefully is nice enough that you can do this average. And of course, how am I going to do this average? I'm going to of course keep the observed data fixed. That's the way it is, and I will of course use my current estimate of the parameter. Right, that's what I'm doing, and obviously this will depend. So there's an x-dependent part of this likelihood function, an x-dependent part of this, which will depend on the unknown parameters. So there is this theta dependence, and this is the theta I'm trying to ultimately optimize over. And of course, it will depend on the current value of the parameters, because I'm conditioning on that when I'm averaging out Z. So basically, that expectation gives me this function Q of the variable we are interested in optimizing over, and it's of course a function also of the version of that parameter that was that we have so far, the estimate that we have so far, that is theta L. And now we have the M step. Now that we have this function of theta, hopefully this is a nicer function to optimize over than the original likelihood function. Why? Because hopefully it inherits the niceness of this log of pxz given theta, right? So hopefully this is nicer. So we just can maximize over it, and this is basically arg max over theta of this q of theta given theta L. And then we go back to the E step, right? So this is, and that's the entirety of the EM algorithm. And what is beautiful about it is that it is guaranteed to converge to a local max of the log likelihood function, basically, of the original one that I'm interested in, right? So that's the beauty of it. So it'll converge to something, and that something will be a local max of the thing we were originally interested in, even though the original thing was intractable. Of course, local is not as good as global, but it is nevertheless a great thing. And obviously, one can do all sorts of hacks around it, like doing a bunch of different randomized initializations and seeing where that goes, etc. So that's the EM algorithm. We'll talk about convergence of the EM algorithm later. We'll sort of sketch a proof of convergence, but let's go back and apply it to Gaussian mixtures and see how we get back the algorithm that we had stated, sort of the sensible and intuitive algorithm that we had stated, just directly. So let's go back to application of EM to Gaussian mixtures. So remember what we had there. My theta was the means, the covariances, and the component probabilities for capital K components, and for a generic data point, my log of P of x theta is this log of the sum, which is a pretty nasty expression that we don't know what to do with, right? So that's the situation here. And what will it take to make this nice? So what if somebody told you which component each data point was coming from? So that is our hidden data. So the hidden data, and for a generic data point, I'm going to write down the hidden data. Z is, we'll take it as a one-hot encoding of which point X comes from. So because if you know that, then you go from this mixture Gaussian to a Gaussian. So that's the essence of this tractability, right? So what does that buy us? So let me just remind you of the one-hot encoding. Z is equal to the unit vector in the kth component, and that's basically 0 everywhere except in the kth component. This is kth element if X is drawn from component K, right? That's what we have. And of course, I know from my mixture model that the probability that Z is equal to EK given the parameters of the mixture is simply equal to pi K, right? So for K equals 1 through K. So that's my setup here. And let me look at now the disjoint density of X and Z given theta. I can write it as P of X given Z theta. What is that? Basically, once I tell you the one-hot encoding, you know exactly which component I'm in. So that's beautiful. That's Gaussian. And then the probability of times the probability of z given theta. And that we know from our model, the probability that z is equal to the kth unit vector is pi k. Now, the beauty of this is both of these can, by virtue of the one-hot encoding, can be written linearly. That's one part of it. And the other part of it is, of course, when I take the log of this product becomes the sum. So log of p x given z theta plus log of p of z theta. And now let's see why this is particularly nice. And I don't need it to be nice in everything. I just need it to be nice in the thing I'm going to average out, the z's, right? So let me look at the second term. Basically, if I want to write this compactly, exactly one of the component is 1 and everything else is 0. So this guy can actually be written as a product by k to the power of zk, the product over all components, right? Because exactly for suppose z1 is 1, then the answer will be pi 1 to the power of 1 times pi 2 to the power of 0 times pi 3 to the power of 0, etc. So the answer will be pi 1, right? So this is gives you exactly the right answer, and so the log of this is also particularly simple, right? Summation k equals 1 to k zk log pi k. So that's that. That's the second term here. Now let's go to the first term. What's that? Well, p of x given z theta is basically equal to the Gaussian density with parameters mk and ck if zk is equal to 1, and basically exactly one of these zk's can be 1 at a given time, right? So basically I can write this, so I can write log of p of x given z theta as zk times log of this Gaussian, right, summed over k equals 1 to k. So because exactly one of these terms can be 1 at a time and everything else is 0, so this is also a beautiful expression. So let me put it together, and let me change the pen color. For a generic example, I have log of p of x z given theta as summation over the components zk times log of the Gaussian corresponding to the kth component plus log of pi k, putting those two terms together. So basically it's a linear function of the one hot probabilities, right? So again, I'm going to do it sort of one example at a time. So if I now take the expectation of this, so the expectation of log of p x z given theta, given of course you're always given the training example, and given some current estimate of theta. If I'm looking at that guy, well, the only thing that happens is I'm going to replace the zk by its expectation, and the other stuff stays the same. So basically it's summation k equals 1 to k. I'm just plugging in the expectation of this given x and theta L, and the rest of it is unchanged. It doesn't depend on z. It depends on the parameter theta that we don't know. So those things we aren't, those dependencies on x and theta we preserve. We are only averaging out the z's. So this is what we need to do. But look at this. This guy can only be 1 for one of these guys and 0 for everybody else at a time. So this is simply equal to the probability that z equals ek given the data point and given the current assignment of the parameters. And that's just this p of k given xi that we had computed before in our when we just sort of stated the algorithm as a intuitively plausible one, right? So basically, this was a p given xi that we had, and we can recompute it. It's just what's the probability of z being equal to ek up front. What's the probability density of x given given that z equals ek? Well, it's just the Gaussian density with the parameters for the kth component, and then of course you have to normalize so that these probabilities sort of sum up to 1. So this is j equals 1 to k pi j n of x given mj cj, right? So the main computation in the E step are these assignment probabilities which we had previously denoted by p of k given xi, and then now we have to plug those in to get my q of theta given theta L. Remember what that was. And now I'm going to bring in all the examples, right? So I have plugged in the assignment probabilities there, and I'm summing over now the training examples. I'm going to put all that together. So for a generic training example xi, I have the assignment probability xi, which is replacing the zi of k. I have the log of the corresponding density. I have the log of the component probabilities. So I have all that. I have to sum this over the components. And now I have to sum it over all the data points. So this is what I have to, we want to sort of maximize this. So if I max this over theta, that will give me my next iteration, right? So that's the thing. Of course, you have to, so not max over theta means I have to maximize over pi k, mk, and ck. And of course, the feasible set for theta is includes this constraint that these probabilities, these component probabilities have to sum to 1. So that's the next step, right? How do I optimize this? But this looks has started looking pretty nice. So the standard thing that we do is to for a constraint is to introduce a Lagrangian. So let me just do that. So j of theta is what I have before, the thing I'm optimizing before. I equals 1 to n, k equals 1 to k, p of k given xi, log of n of xi given mk ck plus log of pi k. And then I have a Lagrangian, I'll put it as minus lambda, but it could be the other one too, but pi k, right? That's the Lagrangian. We are not going to go into optimization in detail right now in the course, so you'll just have to take my word for it that this will work. There's actually and what we'll do is sort of optimize over all the parameters of interest, and you can see that I have to optimize over pi k, mk, and ck, and the terms corresponding to the mean and covariance separate out really nicely. So let me change pen color again. So so mk, ck terms, what are they? They are basically summation I equals 1 to n, summation k equals 1 to capital K, little k, to is pk given xi log of the Gaussian mkck, right? And so you can see that I have, these k different Gaussian problems. So k different Gaussian estimation problems, and I realized that we did not we stated the solution for the Gaussian mean and covariance estimates, but we didn't provide the entire derivation. So, it's pretty plausible that the weights just go over. So, what's the kth problem? The kth problem is I'm interchanging the summation there. The kth problem is summation I equals 1 to n, and now you have different weights for the different examples. But always you basically have the same form as before. So this is a Gaussian parameter estimation problem. Gaussian parameter estimation, where I basically am assigning different fractions of each training example to the different estimation problems, and the answers we have already given before, and I'm going to very quickly remind you of what the answers were. I basically get the mean is a weighted centroid, I equals 1 to n, pk given xi times xi divided by the sum of the weights. And of course, as we noted when we were talking about it first, this can be thought of as an effective number of examples associated with the kth component, and ck is again exactly the same formula that I had, except I have the weights now, different weights now, and xi minus the mean, xi minus the mean transpose, and again I will divide by the same normalization factor, right? Summation I equals 1 to n p of k given xi, right? And so that leaves us with what to do about the component probabilities, how to estimate the component probabilities. And so if we go back to the j of theta expression and read off which parts the component probabilities depend on, let's write it out here. It is summation I equals 1 to n, summation k equals 1 to k, p of k given xi log of pi k minus lambda summation k equals 1 to k pi k. So this is what we have to optimize over pi k. Optimize over pi k. Let me use that notation that we had to make this summation nicer. So recall that if I switch the summations there, summation I equals 1 to n p of k given xi, that's the only part that depends on the training examples, and then outside put the summation k equals 1 to k outside, and then log of pi k here, and then minus lambda k equals 1 to k pi k here. What happened? Basically, I have this effective number of examples assigned to component k coming into this picture, right? And now I take the derivative with respect to pi k. So del by k here is what? It's nk effective divided by pi k, that's the derivative of the log of pi k, minus lambda is equal to 0. What does this mean? That pi k is equal to nk effective over lambda. So it's proportional to the number of the effective number of points you had assigned, and of course they have to sum to 1. So pi k is nk effective over sum over j equals 1 to k nj effective, and we've already seen that these effective numbers add up to the overall number of training data points. So that is my final answer. So basically we have now completed the M step and completed the specification of the algorithm, which is just the same algorithm that we had before, except now it's in the context of we have derived it via the EM algorithm, and hence we can say that yes, this converges to a local maximum of the likelihood function. So it may not be the global maximum, but it has some nice properties. So that will the next step, of course, is to show that the EM algorithm converges in general, and we'll do that next.